Okay, students, now what we covered so far is the basic portion of the communication system. Okay, now if you understand that basic portion, then the remaining communication system, analog, digital, and everything should be very clear. Okay, so now you know the analog modulation technique. What are the different types of analog modulation techniques, and what are the different types of modulation techniques, and how it will be defined? Everything is understand. Okay, now we'll start with the first analog modulation technique, which is nothing but amplitude modulation. Now you tell me the definition of amplitude modulation. What is amplitude modulation? Amplitude modulation is nothing but amplitude of the carrier. The amplitudes of the carrier is varied. The peak amplitude of the carrier is varied in accordance with amplitude of the message signal. Okay, amplitude of the carrier is varied in accordance with amplitude of the message signal is called as amplitude modulation. Now see here. Now with the waveforms I can write such that you can easily understand. Okay. Now this is the message signal, which is the low frequency information. That's why time period is very high. I can write like this. Okay, message signal, which is the low frequency information, means time period is more. Now this is the message signal. Now this message signal cannot transmit it for the longer distance. Then I take the help of carrier. Now this is the carrier signal, C of t. Now this is the high frequency signal, therefore time period is very small, therefore frequency is very high. Now this is the carrier signal of peak amplitude is, this is the carrier signal of peak amplitude is AC plus AC, minimum amplitude is minus AC, peak to peak amplitude is 2AC, and frequency is FC. Now this is C of t, which is equal to AC cos 2 pi FCT plus phi. Now this is the carrier. Now whenever the modulation is done, now what is the procedure for modulation? Whenever any signal multiplied with a sinusoidal signal, now what is the procedure I am writing? First draw the signal other than sine and cos. The signal other than sine and cos is message signal. Then mirror image. A signal other than sine and cos is message signal, then mirror image in the common area frequency of oscillations. In the common area frequency of oscillations. Now this is the Now see here, what happened? The amplitude of the carrier before modulation is AC, which is constant. The amplitude of the carrier before modulation is AC, which is constant. Now, but what is the amplitude of the carrier after modulation? The amplitude of the carrier after modulation is not constant. Is there any change in frequency? No, there is no change in frequency. Now, here I can write frequency of the carrier before modulation is FC. Frequency of the carrier after modulation is also FC. No change in frequency. Phase of the carrier before modulation is phi. Phase of the carrier after modulation is also phi. Then what is the change? The amplitude of the carrier before modulation is AC, which is constant, but amplitude of the carrier after modulation is not AC, not constant, which is continuously changing. Now see here. Now, amplitude of the carrier which is continuously changing. Why the amplitude of the carrier is continuously changing? The amplitude of the carrier is continuously changing. Now see here, message signal amplitude is maximum, therefore here the carrier amplitude is also maximum, V maximum. Here message signal amplitude is minimum, therefore carrier amplitude is also minimum, this is V minimum. So everywhere the message signal amplitude is changing. Everywhere the message signal amplitude is changing, therefore everywhere the carrier amplitude is also changes. So everywhere the message signal amplitude is changing, therefore carrier amplitude is also changes. The amplitude of the carrier is varied in accordance with the amplitude of the message signal, therefore this is called as which type of modulation? Therefore this modulation is named as amplitude modulation. This is nothing but amplitude modulation, AM wave. This is the AM wave in time domain. Now this is carrier before modulation, this is carrier after modulation. This is carrier before modulation. Now this is carrier after modulation. After which modulation? This is amplitude modulation. This is the amplitude modulation because amplitude of the carrier is changing. But this is in which domain? Time domain, time domain, time domain. Continuous wave, continuous wave, continuous wave. Continuous wave modulation, analog modulation, and in that amplitude, one of the carrier characteristic parameter, amplitude of the carrier is varied, therefore this modulation is named as amplitude modulation. This is the AM wave in time domain. Understand or not? So this is the unmodulated carrier and this is the modulated carrier. This is carrier before modulation, this is carrier after modulation. This is the unmodulated carrier, this is the modulated carrier. Now this is carrier before modulation, this is carrier after amplitude modulation. Clear or not? This is in time domain wave. Now see here. Now first of all I want to explain amplitude modulation in multitone. Multitone. What is the meaning of multitone? Multitone means the message signal consisting of multiple frequencies. Now the message signal consisting of multiple frequencies. Let us assume the message signal consisting of multiple frequencies means multitone signal. Now this is the message signal which consisting of multiple frequencies, therefore multitone signal. Now see here, this is in time domain, this is in frequency domain. What is a modulated signal? Now this is S of t. What is S of t? Which is nothing but m of t multiplied with carrier. So S of t, which is nothing but m of t multiplied with c of t. This is generally AM wave in general. AM wave in general definition. in general approach. But what he is saying is, he is saying that AC m of t cos 2 pi fct, this is message signal multiplied with carrier signal. This is message signal multiplied with carrier signal plus AC cos 2 pi fct plus AC. Now this is the amplitude modulated signal. This is the amplitude modulated signal. AC cos 2 pi fct. Now this is AC m of t cos. This is message signal multiplied with carrier. M of t into C of t is a modulated signal. M of t into C of t is a modulated signal. Now M of t into C of t is a modulated signal. But in addition this, now this is an extra term. Okay, this is an extra term, and here he is adding this is another extra term. Now why these two terms? Okay, but he is saying that this is an AM wave, but you want to identify what is this, why this term and why this term, why these two terms are adding. But in general, what is AM wave? In general, the AM wave is nothing but message signal multiplied with carrier. Only these two are the AM wave. But in these two, it is a AM wave. But without this, you are taking that this term is extra and this term is extra, and you are saying this is an AM wave. Okay. Now, how these two terms are coming? Why you add this term? Why you add this term? What is the reason behind adding these two terms? Also we will verify. Okay, we will identify. Now what is Ka? Now Ka, which is nothing but sensitivity of amplitude modulator. Sensitivity of amplitude modulator. This is the sensitivity of amplitude modulator. Units are per volt or per ampere, per volt or per ampere. This is the sensitivity of amplitude modulator, sensitivity of AM, per volt or per ampere. Now see here, this is the signal variation. The signal variation means this is the modulated signal. S of t is a modulated signal. Modulated signal means after transmitter, after transducer. Am I right or not? Therefore, this is an electrical variation. If this is an electrical variation, which means that this is the voltage variation, right? This is the voltage variation. AC, this is volts. Everywhere the unit should be matching. Now this is volts, but this is, here is, what is AC? This is volts. Now what is M of t? This is also volts. So which results volt square. So everywhere the units are volt. Signal is voltage variation. Signal is voltage variation. Signal is voltage variation. Now that's why, now this Ka, now volt square. Therefore this is Ka, the sensitivity of the amplitude modulator. Now this is the Ka, which is the sensitivity of the amplitude modulator. Now this is nothing but volt square. Therefore this is per volt. So what happened? Volt square and this voltage cancel. Voltage variation, voltage variation, voltage variation. Okay. So everywhere the signal variation should be a voltage variation. That's why the Ka is the sensitivity of the amplitude modulator. Units are per volt or per ampere. Volt inverse or ampere inverse. So now see here. But what is the use of Ka? Why the Ka is adding, and all these things we will we are going to discuss. Okay. Now what is the standard mathematical time domain equation of AM wave? So the standard mathematical time domain equation of AM wave is, if you take AC cos 2 pi fct as a common, now AC into 1 plus Ka into M of t, if you take it as a common, into cos 2 pi fct. Now AC cos 2 pi fct, if you take it as a common, AC into 1 plus Ka m of t cos 2 pi fct. Let us assume this is some phi. So this is carrier after modulation. What is carrier before modulation? C of t, which is equal to AC into cos 2 pi fct plus phi. Now this is carrier before modulation. This is amplitude of the carrier before modulation, and this is amplitude of the carrier after modulation. This is carrier before modulation. Now this is carrier after amplitude modulation. So what is the difference? What is the change? There is no change in frequency, right? And there is no change in phase. There is no change in frequency in amplitude modulation. There is no change in phase in amplitude modulation. See, here is also. There is no change in frequency. There is no change in phase. What is the change? Only change in amplitude. That's why this is called as amplitude modulation. Understand? That is why that's why this is called as amplitude modulation. Okay. Now first you note down this. Now see here. Now first we will see the mathematical analysis. Okay. Now S of t, which is equal to AC cos 2 pi fct plus AC Ka m of t into cos 2 pi fct. Now this is the AM wave in time domain, right? Now what is the frequency domain? I want a AM wave in frequency domain because I want to see both the definitions, and also I want to find bandwidth. What is the bandwidth occupied by AM signal? Therefore apply Fourier transform. If you apply Fourier transform, so S of t's Fourier transform, S of f, which is equal to AC, a DC signal's Fourier transform, AC by 2 into delta of f minus fc plus delta of f plus fc. Only one property in the communication system almost. That property is nothing but frequency shifting property, plus AC Ka by 2 into m of t's Fourier transform, m of f minus fc, carrier frequency is fc, plus m of f plus fc, m of f plus fc, m of f minus fc. Now this is AC Ka by 2, AC Ka by 2. So now delta of f minus fc plus delta of f plus fc. Now m of f plus fc plus m of f minus fc. So this is the AM wave in frequency domain, AM spectrum. This is AM spectrum. Now you just see the frequency spectrum. This is the AM wave in time domain. If you apply Fourier transform, now see the signal in frequency domain. See the AM wave in frequency domain. Now, right? F minus Fc equal to 0, F equal to plus Fc. F plus Fc equal to 0, F equal to minus Fc. So, which means that one is plus Fc, another one is minus Fc. F plus Fc equal 0, F equal plus Fc. F plus Fc equal 0, F equal to minus Fc. These are the reference. First we want to take it. Okay. Next. Now m of F minus Fc equal 0. F equal to plus Fc. F equal to plus Fc, which is m of F. M of F is this. Now this 0 is at plus Fc. Now that origin is shifted at plus Fc. Now this is Fc plus omega. This is Fc minus omega. Now m of F plus Fc. F plus Fc equal 0. F equal to minus Fc. Minus Fc plus omega minus Fc minus omega. Now whose spectral amplitude? Now this is AC by 2, right? Now this is AC by 2. Now this is ACKA this is ACKA by 2. This is just a frequency shifting property. Now see here. Now this is the AM spectrum, AM wave in frequency domain. Now see here. Now this is the AM spectrum. AM wave in frequency domain. Now what we can understand here? AM spectrum. Right? And now see here. Now this is the carrier's characteristic parameters are changed in accordance with the message signal is called as amplitude modulation. But now here the low frequency information, now see here. Now the low frequency information is transformed to high frequency. the low frequency information is transformed to high frequency is called as modulation. This is the modulation definition in frequency domain. But why you are finding the frequency domain here? Why you are applying a Fourier transform? For the purpose of identifying the bandwidth. Now there are the frequency ranges identified here. There are the frequencies ranges. Now see here. Now this is the AM spectrum. Then if you observe, the AM spectrum consisting of what? The AM spectrum consisting of three spectral components. First one is carrier, FC, and second one is upper sideband, FC2, FC plus omega. Third one is lower sideband. FC minus omega 2 FC. Now AM spectrum consisting of three spectral components: carrier, upper sideband, lower sideband. Carrier is FC, upper sideband FC to FC plus omega, lower sideband FC minus omega to FC. But first of all, what is the bandwidth of AM wave? Now what is the bandwidth of AM? Now the bandwidth of AM, now this is the frequency components. The bandwidth of AM, which is equal to highest frequency is FC plus omega minus lowest frequency is FC minus omega. Bandwidth of AM, which is equal to FC plus omega minus of FC minus omega, which is equal to 2 omega hertz. Okay. Now this is the bandwidth required to transmit an AM signal. Now which is nothing but 2 omega hertz, where omega is the highest frequency present in the message signal. First you note down this, then we will discuss about the bandwidth and power. Okay. Now see here, what is the bandwidth of AM? Now AM consisting of three spectral components: carrier, upper sideband, lower sideband. Now bandwidth of AM is upper sideband minus lower sideband. Is it right or not? What is upper sideband? FC plus omega minus of, what is lower sideband? FC minus omega. Therefore the bandwidth, which is equal to FC plus omega minus of FC minus omega, which is equal to 2 omega hertz, where omega is the highest frequency present in the message signal. Where omega is the highest frequency present in the message signal, a bandwidth of AM is 2 omega, where omega is the highest frequency present in the message signal. Now for example, if the highest frequency present in the message signal is 10 kHz, now the bandwidth of AM is 2 into 10 kilo, which is equal to 20 kHz. Clear or not? So this is the way you can calculate the bandwidth of AM. Now for what purpose you need to calculate the bandwidth of AM? Because once you know how much bandwidth occupied by the AM signal, amplitude modulation required how much bandwidth, then you choose the channel bandwidth. Now for example, in this case, AM signal will have a bandwidth of 20 kHz, then you choose the transmission channel bandwidth or transmission medium, whatever we are using, guided medium, whose bandwidth should be greater than this 20 kHz. Then only the link is established, then only the transmitter information is going to the receiver. Otherwise, the communication will not be established. Am I right or not? So this is the bandwidth of AM, and bandwidth of AM is nothing but upper sideband minus lower sideband, or carrier, upper sideband, lower sideband are the three spectral components of AM. Okay, note on this AM spectrum analysis, and what we observed here. Now the AM consisting of three spectral components: carrier, upper sideband, lower sideband. The carrier characteristic parameters are changed in accordance with the amplitude of the message signal. Therefore this is called as amplitude modulation, and here the low frequency information is transformed to high frequency as it is. This is available as it is, but which is available at a high frequency. Now this process is called as modulation. Clear or not? Yes. This is the amplitude modulation in multitone. Now multitone means now this is message signal consisting of multiple frequencies. Okay. Now can we see the spectrum analysis in single tone? Yes, we will see that one also. Okay. For this particular amplitude modulation, we will see both. But for remaining things, you can easily have whether it is a single tone or multitone. Not a problem. Now, if it is an analysis for single tone, now what is the meaning of single tone? Single tone means now this type of spectrum is not coming. Now this is a message signal consisting of only one frequency. Now which means that now m of t you want to represent here. What is m of t? Am cos 2 pi fm into t. Now m of t spectrum, m of f. What is m of f? M of t spectrum, m of f which is nothing but am by 2 into delta of f minus fm plus delta of f plus fm. And I have already explained, whenever the signal consisting of only one frequency, spectrum is always consisting of impulses. What is this spectrum? Impulse. One impulse is at plus fm, another impulse is at minus f. This is plus fm, this is minus fm. Now, before this spectrum analysis, then we'll see one small concept. Ka into m of t. What is m of t? M of t is am cos 2 pi fmt. Cos 2 pi fmt. Then this is the modulus. Take the maximum value of this. The maximum value of k into m of t. The maximum value of k into m of t is Ka. The maximum value of this m of t is am. This is 1. So the maximum value of k into m of t is called as modulation index mu. The maximum value of Ka into m of t is called as modulation index. Modulation index or depth of modulation. Modulation index or depth of modulation. The maximum value of k into m of t is called as modulation index or depth of modulation expressed in terms of percentage. The modulation index or depth of modulation, the maximum value of k into m of t is called as modulation index or depth of modulation, generally expressed in terms of percentage. A modulation index is always greater than 0% and the modulation index is always less than or equal to 100%. Generally, this is the boundaries of modulation index, but why these boundaries are like this, we can identify it. Okay, we'll see. Now, mu is less than or equal to 1 and which is greater than 0, or mu is less than or equal to 100% and which is greater than 0% because expressed in terms of percentage. Okay. Now, this is the modulation index, but why importance of modulation index we will see. What is the importance? What is the importance of modulation index? Now we'll see very soon. Okay. Now why the modulation index? What is the use of the modulation index? Why the modulation index comes into the amplitude modulation, and all these things also we can identify. But before that, you just take a definition and equations of this modulation index, and we'll continue. S of t, which is equal to AC cos 2 pi FCT plus AC Ka m of t into cos 2 pi FCT. What is m of t? M of t is nothing but am cos 2 pi FMT. Therefore, S of t, which is equal to AC cos 2 pi FCT plus AC Ka. What is m of t? Am cos 2 pi Fm into t into cos 2 pi FCT. Therefore, now see here, S of t, which is equal to AC cos 2 pi FCT plus AC. What is K into AM? K into AM is nothing but modulation index mu. A modulation index mu into cos 2 pi FCT into cos 2 pi Fm into t. Now this is divided by 2 multiplied with 2 if I do it. 2 cos A cos B. What is 2 cos A cos B? Cos of A plus B plus cos of A minus B. So S of t of AM, which is nothing but AC I will write here, okay. S of t of amplitude modulation signal AC cos 2 pi FCT plus AC mu by 2 into 2 cos A cos B. AC mu by 2 into cos A cos B. Cos 2 pi FC plus Fm into t plus AC mu by 2 into cos 2 pi Fc minus Fm into t. Okay. Now because this is nothing but, now here actually S of t, which is AC cos 2 pi FCT plus AC KAM is nothing but mu cos 2 pi FCT into cos 2 pi Fm into t divided with 2 multiplied with 2. So now this is a signal in time domain, okay. But what I want a signal in frequency domain. I want S of f. What is S of f? AM signal in frequency domain, which is nothing but AC by 2 into delta of F minus Fc plus delta of F plus Fc plus AC mu by 2 becomes AC mu by 4. AC mu by 4 into delta of F minus Fc plus Fm plus delta of F plus Fc plus Fm. Now plus again this one AC mu by 4 into delta of F minus Fc minus Fm. Only one property, which is nothing but frequency shift one, delta of F plus Fc minus Fm. So this is a AM wave in frequency domain, no doubt. Now we'll see in the frequency domain. F minus Fc equal to 0 means F equal to plus Fc. and this is AC by 2 minus FC AC by 2, and AC mu by 4 FC plus FM FC plus FM and minus FC minus FM minus FC minus FM, and F equal to FC minus FM FC minus FM, and this is AC mu by 4 and this is AC mu by 4. Now this is minus FC plus FM. Now see here, now this is the AM wave in frequency domain, but in which domain? Frequency domain, but which is single tone AM wave. This is a single tone AM wave. Now see here, is there any changes here? Yes, this is a carrier, upper side band, lower side band. What is the bandwidth? Now the bandwidth of AM wave, which is nothing but FC plus FM minus FC minus, this is 2 FM, because this is the single tone signal. This is the single tone signal, therefore this is 2 FM hedges. If it is a multi-tone signal, that is 2 omega. Multi-tone means 2 omega hedges. Single tone means 2 FM. FM is the frequency of the message signal, but omega is the highest frequency present in the message signal. Now this is the single tone frequency spectrum, and the previous one is multi-tone frequency spectrum, and this is the way how we are calculating the bandwidth. Okay, but there is no need to find bandwidth for single tone. If you find bandwidth for multi-tone, that will be the final for everything. Okay, now note on this. Now this is S of t, which is nothing but AC cos 2 pi FCT plus AC, K into AM is nothing but modulation index mu, cos 2 pi FCT into cos 2 pi FM into T. So S of t, which is nothing but AC cos 2 pi FCT, is to take it as common, 1 plus mu into cos 2 pi FM into T into cos 2 pi FCT. Now this is the AM wave in single tone. This is the AM wave in single tone. Now see here, this is carrier before modulation, or this is carrier after modulation. This is modulation is completed. Therefore, this is carrier after modulation. What is the carrier before modulation? See here, the carrier before modulation. The carrier before modulation, C of t, which is equal to AC into cos 2 pi FCT plus 5. Now see here, frequency of the carrier before modulation is FC. Frequency of the carrier after modulation is also FC. Phase of the carrier before modulation is phi. Phase of the carrier after AM modulation is also phi. But what is the amplitude of the carrier before modulation? The amplitude of the carrier before modulation is AC. What is the amplitude of the carrier after AM modulation? The amplitude of the carrier after AM modulation is AC into 1 plus mu into cos 2 pi FM into T. Now this is the amplitude of the carrier after AM modulation. This is amplitude of the carrier. This is amplitude of the carrier after AM modulation after amplitude modulation. Now this is the amplitude of the carrier after AM modulation. Now see here, you have some doubts are clarified here. Now this is the amplitude of the carrier before modulation is AC, which is constant. But what is the amplitude of the carrier after AM modulation? Is continuously changing. And this is the maximum amplitude of the carrier after AM modulation, and this is the minimum amplitude of the carrier after AM modulation. Now you can easily calculate it. Now what is the maximum amplitude of the carrier after AM modulation, and what is the minimum amplitude of the carrier after AM modulation? Now see here, from here you can easily identify what is V maximum. V maximum, which is nothing but AC into 1 plus mu. Maximum value of cos is 1, which is nothing but AC into 1 plus mu. This is the maximum amplitude of the carrier after AM modulation. Now, what is the minimum amplitude of the carrier after AM modulation? Now, V minimum, which is equal to AC into 1 plus mu. What is the minimum value of cos? Minus 1. Therefore, this is the V minimum, which is equal to AC into 1 minus mu. This is the minimum amplitude of the carrier after AM modulation and maximum amplitude of the carrier after AM modulation. But each and every amplitude of the carrier after AM modulation is continuously depends upon amplitude of the message signal, because here mu is nothing but K into AM. What is V maximum? What is V maximum? V maximum, which is equal to AC into 1 plus mu. What is mu? K into AM. What is V minimum? V minimum, which is nothing but AC into 1 minus mu. What is mu? Mu equal to K into AM. So every amplitude after modulation is depends upon amplitude of the message signal. So here V1 or V2 or V3 or V maximum is depends upon amplitude of the message signal. When the amplitude of the message signal is changed, a carrier amplitude is also changes. Okay. Now this is the message signal amplitude before modulation is AC. Carrier amplitude before modulation is AC, but a carrier amplitude after AM modulation is continuously changed. That change is nothing but V maximum and V minimum, and this is V maximum and this is V minimum. No doubt. V maximum and V minimum. Now based on this V maximum and V minimum, practically how the modulation index is calculated. Calculation of modulation index practically. Now see here, what is V maximum? V maximum, which is equal to AC into 1 plus mu. Now what is V minimum? V minimum, which is equal to AC into 1 minus mu. If I divided V maximum by V minimum, therefore this AC cancel. So V maximum by V minimum, which is equal to 1 plus mu by 1 minus mu. If you cross multiply, modulation index mu, which is equal to V maximum minus V minimum by V maximum plus V minimum. This is the modulation index mu. This is the way the modulation index mu is calculated practically. V maximum minus V minimum by V maximum plus V minimum. This is the way you can calculate the modulation index practically. Okay. Now, so you know the waveform and we can calculate V maximum, V minimum. Based on that, this is the modulation index. This is the way, a practical way of calculating the modulation index mu. Okay. No doubt.